Welcome to UGC lecture series Linear Integrated Circuit. Today we are going to discuss about the triangular waveform generator, derivation of frequency of oscillation and basics of oscillator. There are several methods to form a triangular waveform generator, out of which we are going to discuss about only two methods. The first one is triangular waveform generator using square wave generator and integrator. So, when you see the circuit, the first stage is a square waveform generator, which is a astable multivibrator. We know that we have already discussed in the previous lectures, the output of the astable multivibrator is a square waveform, and this square waveform, if it is given as the input of an integrator, the integrator generally it integrates the square waveform and gives output as a triangular waveform. So, once the output of the square waveform is given as the input of the integrator, then it will give a triangular waveform. Here the waveform shows that the frequency of oscillations of both the waveforms, that is the square wave as well as the triangular wave, are one and the same. The frequency is same, but the amplitude of the triangular waveform is lesser than the square waveform. This is because of the circuit components connected to the integrator. This R and C must be selected in such a way that the output of the triangular waveform has a maximum amplitude. The next one is the triangular waveform generator using Schmitt trigger and an integrator. This is the circuit setup of the triangular waveform generator using the Schmitt trigger and integrator. We know that the Schmitt trigger also switches the output between plus or minus V saturation, and for the Schmitt trigger, or otherwise known as regenerative comparator, we will give the input to the negative terminal of operational amplifier. Here, instead of giving the input, we have grounded the input terminal, that is the negative terminal of the first operational amplifier is grounded, and the output of the Schmitt trigger is given as the input to the integrator, which is represented as B, and the integrator normally integrates the square waveform and produces a triangular waveform, and this triangular waveform output is fed back to the potential dividers through the potential dividers to the positive terminal of a Schmitt trigger. So, here we have to calculate the effective voltage at the point P, which is given as the input of the Schmitt trigger and which is given to the positive terminal of the operational amplifier A. So, normally we will give the input to the negative terminal of the Schmitt trigger, and whenever the input exceeds the reference voltage present at the positive terminal, the output of Schmitt trigger switches between plus or minus V saturation, and this square wave is integrated and produces the output as a triangular waveform. This is the normal case, but here we are not going to give any input to the Schmitt trigger, which is grounded, and you can imagine that a 0 volt is given to the negative terminal of the Schmitt trigger, and here due to some noise voltage we will be getting initially some voltage at the output of the Schmitt trigger. Say if the output of the Schmitt trigger is plus V saturation, we know that we have given the input signal to the negative terminal. So, the output will be in negative and it is a minus V ramp. We can say the output of the integrator as plus or minus V ramp. It is a negatively going ramp when the input voltage is positive. When you look at the waveform, if V saturation is the output of A operational amplifier, then the output of the entire circuit V naught will be negative going ramp, and you can say this is a minus V ramp. So, this will be given to the one end of the resistor R2, and here this is positive V saturation, and now the effective voltage at the node P is calculated and which is given to the positive terminal. So, this effective voltage, when at one time this effective voltage is lesser than the 0 volt. When the negatively going ramp is given to the other end of the resistor R2, the effective voltage at the positive terminal at one point it will be lesser than the 0 volt. So, in that case the voltage at the negative terminal is higher, and so the output will be now switched back to minus V saturation. If this output of A operational amplifier is minus V saturation, then it is the positive going ramp. When you see the waveform, if it is the minus V saturation or a negative pulse, negative half of the square wave, the output of the integrator is positively going ramp. So, you can call the output as plus V ramp here, and which is given to the 1/2 the resistor R2, and again if we calculate the effective voltage at the node P, then at one time this positive going ramp will go slightly above this reference or slightly above this 0 volt, and at that time, which is the voltage at the positive terminal is higher than this voltage at the negative terminal, and if the voltage at the positive terminal is higher, then the output will be plus V saturation. In this way, the circuit regenerates the output at A as a square waveform, positive plus or minus V saturation, and if the square waveform is given as the input to an integrator, basically the integrator will give for the square waveform a triangular waveform. Or if the question is, if input of the integrator is a step signal, like only a positive DC voltage, a step signal is given, then what is the output of the integrator? Then it is the ramp signal. So, normally the integrator gives a triangular waveform for a square waveform. So, we will now calculate what is the effective voltage at P and how the output of A will switches between plus or minus V saturation, and finally the output of the integrator. Consider the voltage at the output of A as plus V saturation. This is the output voltage of A. In that case, V naught, the output of the entire circuit, will be minus V ramp. So, when you see the circuit, if we want to calculate the voltage at P, that is the voltage at the positive terminal, we have two voltages at the output of A as well as at one end of the resistor R2. Here you have a positive V saturation, here you have a minus V ramp. So, how will you calculate the voltage at the point P? You have to use the superposition theorem. So, consider this is the circuit. As of now, I am considering only the first half of the circuit. So, here this is P. I am taking this voltage as plus V saturation now, and here you have another resistor R2. Here, if the output of A is plus V saturation, here it is minus V ramp. This is the circuit. This resistance is denoted as R3. Okay, R3. These are the potential dividers now. So, the negative terminal is simply grounded instead of giving any input signal. So, the voltage here is 0. So, how will you calculate the voltage at P? Say this is Vp. We want to calculate now. So, by using superposition theorem, consider only for the first case only V saturation is given. For the case 1, only V saturation is given, minus V ramp is not given in the circuit. So, at that time the voltage at the node P will be equal to, so you are using a potential divider rule, this is given and this V ramp is equal to 0 now. So, the voltage across this resistance R2 is the voltage given to the positive terminal. So, now the voltage is V saturation into R2 divided by R2 plus R3. So, take this as Vp1. And what is Vp2? That is case 2. Vp2, how will you calculate it? Here you have to consider, for case 2, you have to consider V ramp is given, that is minus V ramp is given, V saturation is 0. So, for this Vp2 will be equal to, so in this case V ramp is given, V saturation is 0. So, the voltage across this R3 will be the voltage given to the positive terminal. So, here minus V ramp into R3, the voltage across this resistance, divided by R2 plus R3. So, this is Vp1 and Vp2. The effective voltage finally, which is given as Vp1 is equal, Vp is equal to Vp1 plus Vp2. So, what is Vp1? It is Vsat R2 divided by R2 plus R3. And Vp2 is minus V ramp R3 divided by R2 plus R3. And if you look at the waveform, say this is T1, this is T2, this is 0. So, from 0 to T1 it is negatively going ramp. At T1, this is actually the output of the integrator. This ramp is the output of the integrator, but now we are calculating the effective voltage at P. So, during this period 0 to T1, the effective voltage at P will be slightly lesser than this 0. So, you can consider at T is equal to, at the time period T is equal to T1, the effective voltage Vp will be 0. And if you substitute in this equation, say this is 1, this is 2, substitute 2 in 1, you will be getting 0 is equal to V saturation R2 divided by R2 plus R3 minus V ramp R3 by R2 plus R3. And if you simplify this V ramp R3 is equal to V sat R2 and V ramp will be V sat R2 by R3. So, this is the ramp, this is the value of the voltage at the output of the integrator for the time period T is equal to T1. Similarly, when you look at this waveforms at the time during the time period from T1 to T2, then it is actually again the V ramp will be, the magnitude will be V saturation into R2 by R3. This is the magnitude of V ramp at either side of the reference voltage. At either side of the reference, the value of the triangular waveform will be V ramp is equal to R2 by R3 into V saturation. So, this is for one peak. So, if you have the output peak to peak, if you want to calculate, it is simply 2 times R2 by R3 into V saturation. And now, this is the output of, output present here. And now, if you want to calculate the voltage at the output of the integrator, then you have to give the output of the square waveform generator to the integrator's input. So, for that this voltage V naught peak to peak is 2 times R2 by R3 V saturation. Now, we want to calculate the output of the integrator. We have already derived the output of the integrator as minus 1 by RC. These are the two passive components R and C connected to the integrator circuit. Integral of 0 to T by 2 Vi dt. So, this is the formula of the integrator circuit. Now, if you consider this Vi as minus V saturation, because we have seen that either positive V saturation or a negative V saturation will be the input of the integrator. So, now for our calculation, I have considered the input of the integrator for this particular time as minus V saturation, for this time 0 to T by 2 as minus V saturation into dt. So, now this will be minus or 1 by RC, and this minus, if you take it out, then it is plus 1 by RC. V saturation, we know that it is a constant voltage, 1 volt lesser than the supply voltage. If you integrate a constant term, you will have the limit T by 2, and this is V out peak to peak. And we have already derived this V out peak to peak as 2 R2 by R3 V saturation. So, 2 R2 by R3 into V saturation. From this, if you calculate the time period, it is 4 R2 RC divided by R3, and if it is for frequency of oscillation f is equal to 1 by T, it will be R3 by 4 R2 RC. This R3 and R2, these are the resistors which are connected to the schemic trigger, that is the voltage dividers which are connected to the schemic trigger, and this RC are the passive components connected to the integrated circuit. Here this R3, R2 are the potential dividers connected to the schemic trigger, and this RC I have taken it as R and C instead of R1 C1. These are the passive components connected to the integrated circuit. And now we have derived the output of the integrator. Actually this is the output of the integrator as well as the output of the triangular waveform generator, and this is the frequency of oscillation which is dependent upon all the passive components, the resistor R3 divided by 4 into R2 RC. This is the frequency of oscillation for the triangular waveform generator if a Schmitt trigger and cascaded with the integrated circuit. And now we are moving on to the next topic called oscillator, and this is the sine wave oscillator. This diagram shows you the basic system of an oscillator, circuit of an oscillator. Now, if you see the oscillator which has an amplifier, whose gain is denoted as A suffix P, and the output of the amplifier is fed back to another feedback circuit, and which gives the output to the amplifier. This is the basic circuit of sine wave oscillator. If I now redraw this circuit for our understanding, there is an amplifier for a oscillator, and the amplifier's gain is represented as A, and to which the input signal Vi is given, and from here I am taking the output voltage V0 is equal to the gain into the input voltage AVI. If I give this AVI to a feedback network, gain is represented as beta, and the output of this feedback network I am considering this as feedback voltage Vf, which will be the gain of the feedback network multiplied with the output of the amplifier. So, it is A beta Vi. Take this as terminal 1, this is terminal 1 and this is terminal 2. So, if you consider this circuit, the external signal is given as Vi to the amplifier, and amplifier amplifies the signal and produces the output AVi, which is given to the feedback network with the gain beta. The feedback gives the voltage Vf is equal to A beta Vi. Beta is the gain of the feedback network and the input voltage is AVi for this feedback network. So, ultimately the output, that is the feedback voltage, is A beta Vi. Now, if you look at this equation, Vf is equal to A beta Vi, if A beta is made as 1 equal to 1, then this feedback voltage Vf will be exactly identical to the input voltage what we have given to the amplifier circuit. Now, Vf is equal to Vi, identically equal to Vi. So, once the condition A beta is equal to 1 is satisfied, then the feedback network produces the input voltage identically equal to the input voltage. And now, if you connect this second terminal to the first terminal and remove this Vi, now this amplifier A cannot distinguish the voltage Vi which is coming from the external source or from the feedback network, and this amplifier amplifies the input signal and it produces the output with the frequency of oscillation f0 for the condition A beta equal to 1, and this condition is one of the Barkhausen criteria for oscillation for an oscillator. For an oscillator, there are two conditions which must be satisfied by the circuit, and these conditions are called as Barkhausen criteria. One is the condition on the magnitude, the other one is the condition on the phase. The magnitude which we have seen is A beta is equal to exactly equal to 1. Since if it is equal to 1, then the feedback network Vf will produce exactly identical to the input voltage, and this amplifier amplifies the voltage and produces the oscillation. And if the condition is satisfied, along with the condition the phase angle with the loop gain A beta is equal to 0 or multiple of 2 pi, then the oscillator produces a sustained oscillation. It generates the sustained oscillation. And we have considered initially we have considered the input signal Vi. This is only for our understanding. So, we have discussed the Barkhausen criteria. A beta is equal to 1, it must be equal to 1, and the phase shift of the loop gain must be equal to 0 or 360 degree, or it is multiple of 2 pi. The starting voltage is provided by noise which is produced due to the random motion of electrons in resistors used in the circuit. This noise voltage, we have initially considered this voltage Vi. This is actually given from the external source. This is actually not given. This Vi is actually the noise voltage initially which is amplified by the signal, and this if this is given to the feedback network, then this feedback network produces the voltage exactly equal to the noise voltage, and it repeats the action until the oscillation grows on. So, this will be like initially there will be a small noise voltage present at the input of the amplifier, and the oscillations will be amplified and it will be sustained at one time. So, initially it is started with the noise signal and it is growing, the amplitude will be grown and it is sustained amplitude, because the amplitude will not be go on increasing because this amplifier is actually made up of a transistor, and due to its non-linear characteristics of the transistor will go to a saturation level, and the oscillation will also get saturated. The amplitude of the oscillation will also get saturated. Even though it is an amplifier, at one time it goes to a saturation mode, then the oscillation will also get saturated. So, here the amplitude is saturated and initially it is due to the noise, or there is a problem with making this A beta exactly equal to 1 because of the gain will get changed when the temperature changes, or because of the aging factor of the passive components used in the circuit, or because of the change in the supply voltage. Because of these reasons, this A beta will not be exactly equal to 1, it will be less than 1. If it is less than 1, we know that as per the circuit the signal will be reduced, the feedback signal will be reduced, and finally the oscillation will die off. So, we have to make this A beta at least equal to 1 or greater than 1, then only we will get a sustained oscillations at the output of an oscillator. So, in this lecture we have seen two types of triangular waveform generator, and we have derived the frequency of oscillation of the triangular waveform generator using a Smith trigger and the integrator. And finally, we have seen the basics of oscillator, what are the Barkhausen criteria for an oscillator, and what is the concept of producing or generating a oscillation in the circuit. Some questions: discuss the different ways of constructing a triangular waveform generator and derive the frequency of oscillation of triangular waveform generator. These are the references. Thank you.